turns out they captured the whole thing last week's lecture. Okay. My capture of it was, you know, the computer took a hike, but they've got it back there, and so they're gonna put that up on the site. You'll be able to see the rest of it. That's my understanding. Let me know if it happens. I know how that. So. Yes.
Are you gonna be in lab on this Thursday? Are you gonna be in lab on this Thursday?
I have to check my calendar. Is so crazy right now. I think the answer. I'm not going to answer. Let me check. See what is going on. Yes, because I've got a reception that night. Imperial Barrel, but no, during the day I'm here. Yeah. So the answer, yeah, I'll be here for at least the first hour.
You might get some questions.
Good. That's good. But I'm pretty sure that Gulce will not be here because she's right in the middle of that IBA stuff. And yeah, you too. So yeah, right. Okay. So let me start up the Camtasia. Record. Okay. And then from current. All right. Good. Okay. So at last, a subject matter that I actually know something about. Imagine this. So I want to pass around a book that I co-edited back in 86, 87. My co-author has since died, Norman Domenico, one of the pioneers in lab geophysics as related to the second body wave shear waves. And so if you look at the Gassman equations, sometimes you'll see Norm Domenico's name associated with those equations. Gassman equations are the Domenico effect or some of that stuff. I do this because I'm going to be talking about something described by the person I was chasing, and his name would be Robert Garota. In my research days, Robert Garota was a star with Compagnie Générale de Geophysique, CGG. Used to be CGG Veritas, and now is back to just CGG, I understand. They've gone backwards. So anyway, they were CGG then. You can just pass this around. Robert Garota was doing, in that time frame, 80 to 87, 88, about the same thing I was doing, which was two-component seismology, and therefore the title of his text is that. Let me get the lights. So I'll be bobbing up and down. I'll be sitting down and scribbling on the slides, but I also bob up and down occasionally to make a comment. I gave this talk at the request of Western Geophysical about 2 years ago, and then I gave it again at Texas Tech and University of Montana. And since then I've lengthened it, so this is more like an hour talk. It was like 40 minutes at that time. But a couple of comments. First off, multi-component seismology, if you're in 420 like Sean is, you saw Tom Rape talk about this. So Tom Rape talked about what I'm going to talk about, and Robert Garota is the person that we were simultaneously doing some of these same things. And when I talk about travel time inversion, I've got to explain what I mean by that. I'm not talking about first break stuff where you do tomographic inversion of first breaks to get Earth models, which is a neat thing. I'm talking about measuring Poisson's ratio, which turns out to be a function of the VP-VS ratio and nothing else, as one definition of it. And when I say VP-VS ratio, I mean if you have an interval velocity compressional wave and an interval velocity shear wave for the same interval, then you can measure elastic properties if you have one more thing, and that's density. If you don't have density, then you can still get Poisson's ratio, and that's a heck of a tool. And let me emphasize that Poisson's ratio, that measured quantity, tells you a whole lot about lithology, pore filler, elasticity, a lot. And that's what Robert Garota's text is all about. He and I were both experimentalists using both body waves for this, and that's what you're going to see here. So travel time inversion, I mean specifically, and then let me elaborate further. So you say, well, how'd you get the velocities? I don't get the velocities. I take common midpoint gathers that have been moved out to a stacked trace. And if you have coincident stacked traces, the distance is identical. The T0, okay, it's identical. So VP over VS, that ratio can be accomplished by TS over TP, where TS is simply the measured interval travel time, and TP is the measured interval travel time for a shear wave section and a P wave section for which you have identified that's the same event. That's called registration. So registration is quintessential to the continuing of using both body waves. So you don't have to get velocity. You can say, hey, there's picture A, there's picture B. Those are the same events. You frame it. You measure the interval travel times for a particular shot point. Ratio the two. TS over TP is the same thing as VP over VS. You just do the arithmetic. It's just it turns upside down on you. And from that you can get Poisson's ratio. So that's where we're going. That's where we're going. Okay, so that's the subject matter. So let's go to the Zoeperts equations, and let me get this working for me here. And one more thing, and that is here. Okay. So in the Zoeperts equations, this old picture of some old equations, here I've got a P wave. Why do you know it's a P wave? It's got A, right? Not B, alpha, beta for P wave, S wave. Okay. You got a P wave hitting an interface between two elastic materials. And for each of the two materials, you've got the compression wave velocity, shear wave velocity, and density. And if you've got that, you've got everything, right? From compression wave velocity, shear wave velocity, and density for either material, if you have that, you can fully describe the elastic properties. So I've got a P wave coming into a boundary between two elastic materials. What we're going to be looking at is two things. First is we're going to be looking at that is converted to a shear wave. And so that's called a converted wave or a PS wave. It's P down, S back. You'll have to forgive me, I got a couple stories along the way. Stanford prof, why can't I say his name? I can't say his name. I'll think of it. I'll think of it. Okay, let me just leave him. Probably I shouldn't say his name because I'm going to say something kind of crazy about him. There's a Stanford prof who is quite famous and has been famous for quite some time. And he was pretty good for one-liners. And he said you could not do migration in the Fourier domain. So then my boss, Bob Stolt, wrote the famous paper in '76, Migration by Fourier Transform. And John Claerbout, I couldn't say his name. John Claerbout said, wow, that's impressive. Come out and run my program for a year. I'm going on sabbatical. So about 2 years after that, Bob Stolt continued to have conversations with John Claerbout. And John Claerbout said, there's no such thing as converted waves. So it was kind of fun to send John Claerbout in plain brown wrapper some of our converted wave sections and let him once again witness the problem of being an authority on all things known, because that's not his line of work. The other thing we're going to talk about is if I replace this right here with a shear wave, and it's a particular kind of a shear wave. So if I have, this is the interface here and I'm going to hit it, and if I got a P wave, it gives a P wave back and an S wave back and a P wave down and an S wave down, all that stuff. If I hit it with a shear wave that has this polarization, okay, it's going to smack that interface at any angle, and the polarization is parallel to that boundary. It turns out you don't have any conversion, okay? You don't have that continuity equation such that you'll convert to anything else. So they call it a pure shear wave. So that if I replace this with a shear wave that has a polarization that's like this, okay, on that boundary, then you're just going to get shear wave out and shear wave down, no conversion. They call that a pure shear wave. So you're going to see examples of that. You're going to see a mode converted shear wave, P in, S out, and you're going to see SH wave in and SH wave out. Those two things. And of course you'll see P waves too, P waves in, P waves out. Okay, so let's go to the Conoco shear wave group shoot in the 1970s. And this was the first time that various oil companies got together to address a common project with the idea of sharing resources to see, let's get to the bottom of the shear wave thing and see what we can do with this. And so the shear wave group, I worked for Sun Oil Company during this time, but there were all the majors there, Shell, Exxon Mobil, except it was Exxon and Mobil. There's two different companies and you name it, they were all there. Amoco, on and on. 33 companies I think were involved in this. We looked at 20 sites around the western United States, and there are the sites, and we had a whole lot of different interest in looking at these sites. In other words, 8 of the sites had a porosity development and so forth and so on. You can see right there. Okay, for the Conoco shear wave group shoot, we used a shear wave vibrator, okay? And here is the business end of the vibrator. And very much like your standard vibrator, it vibrates when you set up a sweep. The only difference is this vibrator would vibrate left to right as opposed to up and down. And it had little, you'd plant it in the ground. First time it weighed 55,000 pounds. You'd plant it in the ground and shake it left to right. And what are you imparting? A horizontally polarized shear wave. The so-called pure shear wave that goes down and comes back is nothing but a shear wave. That's why they use that particular polarization. Let me put a little caveat there. If your if your elastic material is anisotropic, then no matter what you put in as a polarization of a shear wave, what will come out of that is the two shear waves, fast and slow, associated with that anisotropy, irrespective of what you put in. But for homogeneous and isotropic materials, which for the most part, earth materials are. If they are anisotropic, it's only mildly so. But, okay. If that's the case, then everything's off. All bets are off. But if it's homogeneous and isotropic, a shear wave in stays a shear wave out. It stays the same. Okay. Now there were other shear wave techniques. Here's a fun one. This you can see this one had a safety problem. This hammer is on its way down, and it comes down and smacks this plate. And if you made the mistake of getting between the hammer and the plate, you were history. This is in the Black Forest. These gentlemen are standing there. You can see the other problem with this hammer. And these guys are with Compagnie Générale de Geophysique. This is their weapon, as I called it, called Marthor. The French are quite romantic. And so Marthor comes from the two gods of the hammer, Martheus and Thor. So they made Marthor this creature, and it would really smack the ground and give you one hell of a good shear. And again, it's a horizontally polarized shear wave, so it's a pure shear wave. Now, to be sure, I mean CGG is an awesome company. They're still around. Come on, and they made a later model of it that was very clever. It pivoted on itself and inside of a cage, and so you took away the safety problem. And you made it a smaller hammer and you hit it more times. Because see what they were doing here is they were ripping the earth. So it wasn't a clean elastic transfer. You create a lot of inelastic energy. So that's not a good thing. You hit it too hard.